Hey everyone! Today I want to tell you about my recent visit to ASML, a large tech company in the southern part of the Netherlands. They've been in the news quite a lot lately, mostly because of the export restrictions that the US has imposed on them, and this is basically to prevent export of their machines to China. Now, the reason for the restrictions is that ASML produces so-called wafer scanners, which are machines that are used in the manufacture of microchips. Now, in this video I'm not going to discuss politics or chip manufacture in general. I just want to take a deep dive into the imaging that is at the basis of photolithography. I guess you're all familiar with the constant race to shrink the size of electronic components such as the transistors on microchips. And compared to 50 years ago, the current transistors are now 1,000 times smaller. The manufacture of a full chip is a very complex operation involving many steps such as the deposition of layers, etching, baking, implanting ions, but there's one step in the manufacturing process that drives the miniaturization, and that is the one done by the machines that ASML produces. The task that these machines perform looks deceivingly simple when you look at the principle, and in a way it's quite similar to the process behind analog photography. So in order to create a pattern on a microchip, you use a light source, a mask containing the pattern, and a lens system that projects the image onto a light-sensitive film, which is called a photoresist. And basically, this is the only task that the wafer scanner performs, doing exposures with light. Everything else in the process of making an integrated circuit is done somewhere else in the chip factory. Now, even though the principle of operation is very simple, the price tag of these machines indicates something else. The latest generation of ASML's machine have a purchase price of around 170 million euros apiece. To put that into perspective, the money for just one machine could also buy you a complete residential area with 400 family houses on it here in the Netherlands. And in addition to the purchase price, they cost several millions per year to operate. But the flip side, of course, is also that they're extremely valuable to the companies that manufacture chips. Somehow all that money can be earned back with the one process step that they perform. Now, this is only possible if the machines have a high throughput and the task that they perform has very high added value, because that's the only way that you can justify such huge investments. The technology has now reached a point that the smallest features produced on a chip can be as small as about 12 to 15 nanometers wide. And I know that the so-called technology nodes name numbers of 5 or even 3 nanometers, but those numbers aren't actually about physical feature size. They're more about, let's say, the general process accuracy. Even so, it's quite hard to appreciate how small 12 nanometers really is, but let's give it a try. Here is the processor of my first real PC. It's an Intel 486, which was manufactured in 1992, so it's more than 30 years old. With the naked eye you can see distinct areas like the cache memory and some colors of light being diffracted, but that's about it. It's only under a microscope that you can get an idea of the amazing complexity that this chip contains. So here's the chip at the lowest magnification, and it's still difficult to see individual components. But when you increase the magnification a bit further, then more details come into view. By the way, what always amazes me is the combination of the high resolution and the area over which it is achieved. So to make this chip work correctly, the placement of every single feature over the full area of the chip should basically be perfect. And it's not difficult to imagine that in order to make this chip, you need a very high accuracy for positioning the different layers, and also a pretty special lens with a high resolution and field uniformity. Now let's get back to the 12 nanometers. To see the smallest features on this chip, you actually have to go to quite high optical magnifications. And that is because the smallest features are around 1 micron. For example, these little circles, which I think are vias that connect the different conductive layers, are about 1 micron in diameter. But 1 micron means 1,000 nanometers. And if I now draw 12 nanometer features to the scale of just a single via, this is how they would compare. I personally find this completely mind-boggling, and I hope that this comparison gave you at least some frame of reference of how small the patterns are that can currently be made with state-of-the-art photolithography. So let's go to ASML and find out what it takes to create images with light on such a small scale. After my arrival on the ASML campus, I was met by my host for this day, Sander Blok, who is an imaging engineer, and he was also the one who invited me over. So after a coffee with some of his colleagues and lunch, we went to visit the ASML Experience Center. Now this is a pretty amazing place where any geek would love to take their Tinder date to, but unfortunately it's not accessible to the general public. This is where they showcase some of the technology, mostly from an historical perspective, and it's here that I discussed imaging with Sander. But of course, I was also curious how he got into the field of imaging.
I worked on the hardware to support building the machines here in the factory. So when we're building the machines in the factory, because our machines are so incredibly complex, always something goes wrong and then someone needs to fix it. So I helped, especially on the optical column. And then while working on the optical column, I wanted to know, why do we have this? What's the functionality of this? Started studying that during the evening hours when no one was calling me. Learned a lot about imaging, image formation.
So actually you were not an optical engineer or imaging engineer by, let's say, education. You just learned it while working here.
I was more working on electron transport, mesoscopic physics and so on. So everything I learned, I learned here about optics.
Yeah. Okay. And so what is it, what is the aspect of this incredibly complex machine that you're working on at this moment? So what kind of problems, what kind of subjects do you work on?
So I don't actually work on a specific module, right? So I work with the optical column. Our machines are imaging machines. They produce images on the wafer. And now I'm looking into what causes this, what's the physics behind image formation? How does it work? And is there some way that we can enhance it? For example, can we change the mask in such a way that we can lower the dose? So this means if we lower the dose, you can get faster throughput. Or can we enhance the contrast? Are there things that we can work on, smart tricks, to enable scaling, to really drive scaling? And then it's really every aspect from imaging. So it's from the mask, can we do something with the illumination? Maybe we can inject some aberrations to actually have better performance, all these kind of things.
Okay, that sounds very interesting.
Yeah.
Okay, so let's pause here for a second. During the afternoon we talked about a lot of things, and for me as a nerd with a fetish for optics, it was all super interesting. But at the same time it was also quite overwhelming. So when I was making this video I had to make some tough choices what to talk about, otherwise I would definitely overwhelm a lot of viewers too. So instead of trying to tell you as much as possible about everything, I decided to instead focus on what I found is the most fundamental realization that this visit gave me. And that is that imaging at these scales means managing diffraction. Now this is a pretty difficult subject, so to make it a bit more accessible, I decided to try a very visual approach and to use wave animations. Because when the size of the features that you're trying to image is in the order of the wavelength of the light that you use, suddenly everything revolves around how light behaves as a wave and about diffraction and interference. As for the animations that I will show you, these are a serious simplification of light as a 3D phenomenon in space, but also of the optics. So the way that it's displayed is as a 2D representation, basically sort of a cross-section of the field. And the 2D representation also means that I will just show one field component of the electromagnetic wave. So you could consider this, for example, to be the electric field component. Now I have generated basically two types of animations. One that shows the actual wave behavior with the field amplitude, wavelength and phase, and the other one that visualizes the intensity of the radiation in space. And intensity is actually what we measure when we detect light with a sensor or when we expose a photoresist layer, and the intensity can be calculated by taking the square of the amplitude of the field. I want to start out with something simple. Just a short row of point sources spaced at equal distances and emitting light coherently. Close by, the interference pattern looks kind of complicated, but if we look somewhat further away from the sources, so in the far field, we observe that the wave energy is actually concentrated in a few specific directions. This is especially clear if you look at the intensity distribution. Now, the reason behind this phenomenon is in the ratio between the spacing of the sources and the wavelength that they emit. So on average, the waves mostly interfere constructively in specific directions where they are in phase, and they destructively interfere in others. And what we can do is assign diffraction orders to these directions. And the number here indicates the difference in wavelengths between two neighboring sources in the direction at which constructive interference is observed. If we now make the sources emit a shorter wavelength, the angles between the different orders becomes smaller, and so they're more tightly packed together. And this is what you can also observe in the current simulation. If we now keep this wavelength the same but decrease the distance between the sources, we observe that the angle between the different diffraction orders is larger again. And in this example, you can observe that the first order interference maximum is under quite a large angle actually. And so a lot of the energy contained in the radiation is emitted under a large angle. So why is this relevant for imaging a pattern from a mask? Well, with the chip patterns used in photolithography, we can observe something similar. Say that we have a mask consisting of lines and spaces, which we illuminate from the back and that we want to project to an image. Now, the edges of the openings in the mask will also diffract light in different directions, and since there are a lot of small features on such a mask that have comparable dimensions, we can also distinguish different diffraction orders, especially for the smallest features. For features that are quite a bit larger than the wavelength of light, most of these orders will be under relatively small angles. But with decreasing feature sizes, more light is being diffracted away under higher angles. Now, the reason that this is a problem was also discussed in my previous video on image formation. But the bottom line is, you cannot create an image from just zero order diffraction. To generate the interference pattern required to recreate the pattern on your mask, you need at least a combination of zero and first order diffraction. So let's add a projection lens to the setup and take a look at what this means in practice. So here is the new setup. On this side is a mask with equal lines and spaces that transmits light coming from the left. The transmissive mask has 6 openings, which are quite a bit larger than the wavelength of light. Furthermore, we have a couple of lenses intended to project this pattern onto a focal plane. Now, just to be clear, the design of this optical system really sucks, and it does in no way do justice to an actual optical system. For example, it has terrible spherical aberration, but nevertheless, with this lens, the 6 sources can easily be resolved in the focal plane. Now, to show you that we're actually resolving the individual openings in the mask and that it's not some random diffraction pattern, we can close up one of the openings and look at what happens on the other side. And what we observe is that these light sources are indeed imaged one on one. When we make these features smaller using the same wavelength, we observe that this system cannot resolve the individual details anymore. And the reason is that the majority of the first order light is now diffracted under quite a large angle, thereby missing the aperture of the lens. And this makes it impossible to recreate the details of the pattern in the focal plane. Now, to get the first order diffraction back into the pupil of the lens, we could of course use a shorter wavelength or use a larger numerical aperture lens. But what if we are already on the limits of what is practically feasible here? Then there's nothing we can do about it, right? It's just physics. Well, maybe there is something we can do. So what do you think would happen when we put the light projection system under an angle, such that the zero order light still goes into the pupil, but we also allow a significant part of the first order light to go into the lens? Now, if you try that, this is what happens, and I must say, to actually see it in action is pretty amazing. We observe that now we suddenly can resolve the individual sources again. So, as long as we somehow collect the light of these 2 different orders of diffraction, we can apparently recreate an image of the 8 individual sources. Now, just to be clear, this is not about placing a mask under an angle, because that would create all kinds of other challenges in the optics. We actually only have to change the angle of the illumination, because the light actually contains the phase information that allows for changing the angles of the different diffraction orders. And this is also true for non-coherent radiation, because a field is basically a linear superposition of waves, and it's always every wave for himself. So on the walls of the Experience Center you can find this formula that captures the essence of everything I've shown in the animations. And not accidentally, it's also the foundation of all the work that's done here in the field of imaging. It says that the size of the smallest feature that can effectively be imaged, also called the critical dimension, is equal to a parameter called K1 times the wavelength of the light, lambda, divided by the numerical aperture of the imaging system. And if your critical dimension is small, the diffraction will fall outside of your lens, so we can either decrease the wavelength or increase the numerical aperture of the lens. Both will allow smaller features to be imaged. But what about this K1? Well, that parameter is about trying to find where the limits are of what's practically possible. As we just saw, one way to decrease the critical dimensions further is by tweaking the illumination field. And so the value of K1 combines every clever trick that you can come up with to further decrease the size of the critical dimension. Tweaking illumination is actually the most powerful tool that the ASML machines use to squeeze out every last bit of performance. So instead of just straight on illumination, the light can, for example, be generated in a cone shape. And this results in a uniform field, but one that only reaches the mask under a specific range of angles. Or you could tailor the light such that it best matches a specific pattern on your mask. If, for example, your pattern is just lines and spaces in one particular direction, you might actually be better off by just using light from two very specific directions. In fact, you could tweak the angular distribution of your light to a very high level of detail for every single pattern. But in fact, the tweaking does not stop with detailed control of the illumination. It's also possible to further optimize K1 by what is on the mask, because in principle we don't care what's on the mask, we just care about the image reaching the wafer. So here's an example of this. Say we want to image this pattern. Then we can use a mask with the same pattern and optimize the angular distribution of the illumination field. But if you look at the resulting aerial image, so the way that it is projected, it's not that great. Now what we can do next is optimize both what's on the mask and at the same time optimize the illumination field to give us an image on the wafer that most closely matches what we actually want. And that is displayed here. Now what you can observe is that both the mask as well as the illumination field are completely different from what you started out with. But who cares? In the end it's all about what's on the wafer. Now this type of optimization is part of what is called computational photolithography, and it's actually a whole field of research on itself. If you look at a picture of a conventional deep UV stepper, you can actually observe how important illumination is. Here is the stage with the wafer. Now this is the projection system, and somewhere here is the location of the mask. And all of this here is just there to massage the light such that it best suits what you want to image. In other words, it's all there to minimize the value of K1. So far in all the examples of the wave simulations I showed transmissive masks, but the latest generation of machine uses extreme ultraviolet light, or EUV, with a wavelength of only 13.5 nanometers. Now, from the viewpoint of critical dimension, it really makes a lot of sense to use a wavelength that is 14 times shorter than that of the previous generation of machines. But from the practical perspective, it leads to an almost insane complexity. So let's hear what Sander has to say about EUV photolithography.
EUV is incredibly hard, and it's really if you're pushing the envelope like we are, there are a lot of trade-offs that you need to do, and there are a lot of things you need to take into account. Probably one of the hardest things that you need to do is that everything absorbs EUV, so therefore you need to do everything in vacuum. And that adds a lot of complexity because suddenly you need a vacuum chamber around your lithography machine.
A vacuum pump, which vibrates and stuff.
Exactly. So I haven't even thought of that. But yes, and if you have vibrations, if you're working on the sub-nanometer scale, you really need to think about this. And so there are many, many different complications. For example, load locks to get the wafers in and out of the vacuum. And if you need to get the throughput of like 160, 170 wafers per hour, your load locks need to be extremely fast. So these are all non-optics things. Of course, you have to have the optics, right? So the only way to make a little bit of reflective optics is with reflective multi-layers, so Bragg reflectors. Now, the reflectivity of a Bragg reflector is strongly angle dependent. So this means that you need to take into account your angular distribution of light because this angular distribution needs to be within a certain limit. That's one thing. Another thing is what you mentioned on the mask. In order to get light through your optical system, you need to be at an angle, otherwise you reflect light back into the previous element. On the mask, it's a three-dimensional object, right? So this means that the mask where your pattern is defined, it also has a reflective multilayer. Light, on average, travels some distance into the multilayer before it reflects. The absorber that absorbs the light, so the dark lines, it normally, chrome on glass, so a thin layer. But here they're quite thick, and they're comparable to the feature size. So you have stuff like shadowing. It's also that you get diffraction on the way in, and then you get reflection, and then you get diffraction on the way out. So you get double diffraction. And all these things, they add phase effects and all these things. And they complicate things quite a lot, but it's also a challenge. Like, can we invent stuff or think of new ways that we can deal with these kind of things? And that's also what makes it interesting.
Yeah.
One thing that became clear to me about extreme UV photolithography during my visit is that it is extremely difficult. It's extremely hard to make UV light. You need a megawatt laser shooting pulses at tiny droplets of tin metal 15,000 times a second. It's extremely hard to manufacture the reflective optics so that you can create nanometer-sized features on a chip. It is extremely hard to synchronize the movements of a mask and a wafer to nanometer precision over all 6 degrees of freedom while they are constantly accelerated at 30G. Not to mention the electronics and the software that need to orchestrate this all. And all of this just intended for that one special moment in the life of a photosensitive layer. So with this I want to end my video. I want to thank Sander Blok for the invitation and the interesting discussions. I also want to thank Mark Assink from Public Relations, who organized things in the background, also related to filming. And last but not least, I want to thank Manuel from the channel Diffraction Limited, who supplied me with the code to make all the wave animations. If you want to try this yourself, then go check out the link in the description. And of course, I want to thank you for watching.